For today's video, we're going to be running DeepSeek R1, the full DeepSeek 671 billion parameter R1 model locally on a perhaps enthusiast-grade desktop PC. Now, I'm basically just going to jump right into this, and we can see first and foremost that the terminal here on the right side of the screen, we're seeing some output, and this is actually going about making a Flappy Bird game. This is the full 671 billion parameter DeepSeek R1 model running locally on my machine and actually outputting all of this text at an acceptable token speed, I would say, for the size of this model. Now, the whole reason this is actually possible is thanks to the intelligent folks at Unsloth AI here. They were able to put some, I suppose you could say, magic in place and actually shrink down the original 720 gigabyte file for, or not file, but 720 gigabyte size of the DeepSeek R1 model into 131 gigabytes. Now, I don't want to get hyper technical in this video. I would like this to just be more of kind of a technical demonstration / exploration, but they did use something called a dynamic quant, or this is a dynamic 1.58-bit quantization. Now, I would like to give a brief explanation of how this actually works, but I would like to do so in perhaps a metaphorical way that could be applicable to a more general audience, if you will. And for that, I do have a small helper here. And this is a Best Buy ad, probably from like 2008 for the Toshiba Quasmio, which is, of course, my favorite gaming laptop, which is behind me on the shelf, but I don't think you can see it. So basically, the whole concept of this dynamic quant is basically taking something and making parts of it much smaller, but keeping the important parts of it slightly less small so that it still is able to be lucid. Now, to use this picture to actually kind of make this example make sense, let's say I have this saved on my computer and I need to email it to someone, but the file is way too big to be emailed, so I need to shrink the photo. If we see on the screen right here, where they say we tried just doing a full 1.5-bit native quantization of the entire model, it breaks it entirely, causing endless loops and gibberish. That would be akin to taking the image file of this on my local machine and just shrinking it down a lot. It would unfortunately make the text illegible, as well as the whole photo would become far more grainy and harder to see. It would be smaller, but it wouldn't be very usable for our purpose. The whole kind of idea of this dynamic quantization is as follows. Let's say that the person I'm sending this to just needs to read this kind of paragraph right here, not even the top text or any of the lower text, just this right here. We will basically selectively look at this portion of the image and shrink it, but not as much as we will shrink the rest of the image. So basically the photo of the laptop, the background, and then this big kind of advertising text up here will become blurry and perhaps not legible, but for the purpose of what we need, that's totally fine. However, this little paragraph right here, which we need our recipient to actually be able to read, will stay sharper and a bit more legible. So the entire photo will get smaller as a whole. However, the important section will stay a bit bigger, while the less important sections will stay a little bit smaller and less legible, because for what we need it to do, that is totally fine. That is kind of the whole idea of this dynamic quantization. And if you are perhaps familiar with quantization, like you've used llama to download a 4-bit quant of a llama 3 model or something like that, basically what they say here is when they try to do a 1.5-bit native quantization for all layers, it just makes the whole model like blurry. And basically it's the same thing as if we just kind of made this whole picture shrink down a lot and it was impossible to read any part of it. I hope that kind of makes sense. And again, when I do explanations like this, I like to think of them as like non-scientific. So don't like try to judge it like that part wasn't accurate or da. And the reason I say that is so that I can continue to make myself seem intelligent, but if I make a mistake, it doesn't look bad. No, I'm kidding. But I just like to give kind of more like good enough examples, if you will. With that out of the way, let's kind of just take a look at a bit more of this. And following that, what we're actually going to do is just not a full tutorial, but I will show you how I actually managed to get this running on my system. if we scroll down, we do see there's some math and things like that, which for this video, we're kind of just going to comb over. But they do also mention actually running this in VLLM or llama. I have actually tried both and did not have good luck with it. So what I did end up doing is just running it with llama.cpp, which is also kind of specified here. And for like the next step, I suppose you can say, we are actually just going to run through the actual process of how I got llama CPP set up and able to actually run this model. Now, if we look up here into the table, there are a few different versions of dynamic quants of this model that these folks actually did upload to Hugging Face. So there is the 1.58-bit, which is the 131 gigabyte size one, which I have actually running here in the terminal. And if we click on this, we will see the Hugging Face page opens for it, and it is two 50 gigabyte downloads and one 41 gigabyte download, around that. There are some bigger ones, so if you have a little bit more memory available on your system, you could perhaps run some of these, and we can see the quality. However, the smallest one here, and I say smallest with a grain of salt obviously, is what we're running right here, and we are actually just kind of following the same exact sample here, where you can see the original DeepSeek made this kind of game of Flappy Bird, and the 1.58-bit quantization version made this. And what this is doing right here is actually, it's doing that. So we can see from where we started, there should be a think tag. So we can see that there is the opening think tag. And again, this is the full version of R1 from DeepSeek. So basically they're comparing this example to what you would see from chat.deepseek.com, which this is wild to actually be able to run this locally on your machine or my machine or whatever machine, if you will. And okay, so we have it here. Let's see, it is doing Pygame to actually make it. And its thought process, I know some folks took a little bit of issue with that. Sometimes I don't read like all of the output or the prompts. I'll try to kind of go over them more, but I find that it would take me far too long to actually read this all on camera, and we would probably both fall asleep. So, but you can just kind of see its thought process and things like that. And again, for the quantization and the fact that this model was shrunk down 80% in size to still be outputting lucid thoughts like this and things of that sort is really quite cool. And I think it brings a lot of excitement to perhaps some of the actual future advancements in being able to run more intensive AI models on perhaps less intensive or specialized hardware. Really, I'm going to kind of just let this go, and then I'll see how it ends up finishing this, and we'll see how the example does compared to what we see here. This blog does a really cool job of giving a light but intricate kind of look at how this all went together and worked and things of that sort. But overall, it's not actually that difficult to get running, assuming you do meet that 80 gigabytes of total available RAM threshold, which I understand can be kind of a lot, but for a enthusiast with a local LLM machine, it may not be so out of reach as running the full 720 gig DeepSeek would have been. So while this is still running, I do kind of just want to give a peek into the actual system utilization in terms of the performance metrics. So right here we can see the utilization of the CPU and the system RAM. So it is very heavy on the CPU right now and on the system RAM as well. And system RAM, for what I'm referring to right now, is actually the physical RAM sticks in the motherboard and not the video card RAM. I did actually have to, this only had 32 gigabytes of RAM in it, which has been like kind of abysmal for the system for a while. So I swapped it over to 128, and I had to like wiggle all the RAM sticks in and out of there without actually like taking the liquid cooling system apart. And I was definitely knocking some of those pipes around, but it was it hasn't leaked at all. So that's a good sign, and knock on wood, it won't. If I go here into the graphics card utilization, we can see that card 0 is using around 21.5 gigabytes of video RAM, and card 1 is using around 21. So overall, this is extremely performance intensive. However, it is just cool that this is actually running on the system. I had been interested in this model for a while, but I figured there was absolutely no hope of me being able to run this on any computer I owned without having to go spend a bunch of money to get new hardware and things like that, which I just was not kind of in the cards, especially just to run one model, no matter how cool it may be. But this is really cool, and I noticed that I have seen more and more builds popping up that perhaps just use like DDR5 memory and lots of it and some fast CPUs to actually run LLMs, and kind of they omit the entire GPU thing from the whole system, and folks do it. You can see here it's not necessarily fast, but depending on what you're doing, that may actually be okay. We can see that it is appending pipes here. I've now gone ahead and deleted llama.cpp from the system, and we are basically going to now together go ahead and just follow the steps that I actually took to get this working. Basically, from the blog post here for the actual R1 dynamic quant from Unsloth, if we scroll down here all the way to the point where we can see running dynamic R1 quants, we do see the instructions to actually get this working with llama.cpp. To begin, we are just going to basically follow the commands listed in this sequentially. If you go ahead and type this, depending on how your system is set up, you may see an error or a permission error. If you do try to run that and you see that error, just append sudo to the beginning of that command and then press enter once more, and that will just run it as root or super user or with elevated permissions, I suppose, if you want to put it somewhat simply. The next thing you're going to want to do is to install some of the dependencies that you will need to actually go ahead and build llama.cpp. And again, if you were to run that without sudo, you could get that error message. So I am just going to once more append sudo to that command. I do already have these installed, so my machine is just going to tell me, hey, you already have these. However, if you're doing this for the first time, it will go ahead and download and install those for you. The next thing we are going to do is just clone the GitHub repository for llama.cpp to our local machine by running this command right here. And once we do this, well, once it completes, if we type ls to just list our directories, we will see that we now have a llama.cpp folder, which is where the cloned GitHub repository has ended up on our local machine. You will just see me clearing the terminal a lot. Just ignore that. I'm just doing that so the old text doesn't kind of overwhelm our viewport, if you will. The next thing we're going to do is run this, which is actually one entire command. So basically everything following the git clone command would be run at the same time. I do want to point out a few things here. They do hyperlink the actual build instructions for llama.cpp here, and I am running this command as it sits here because I do actually have an NVIDIA graphics card on my machine and things of that sort. If you are attempting to do this on a machine with a different configuration, perhaps you don't have an NVIDIA card or something like that, I would just kind of recommend taking a look at these actual build instruction documentations. And really, if you find yourself a little stuck in, okay, like this is quite overwhelming, which of these flags do I append to actually build this for my specific system? I would honestly copy this command right here, put it into your favorite LLM and say, using this as a reference, can you please tell me what I need to do for my specific system, and then tell it your system configuration. And then you could basically also send it all of these options, and it will likely tell you the correct way to actually go ahead and build llama.cpp for your system. That is the one thing out of the way, one of two. The second thing is we need NVIDIA CUDA toolkit installed as well. So basically, if you type nvcc version and you don't see anything show up, you need to go ahead and install NVIDIA CUDA toolkit. If you just run apt install NVIDIA CUDA toolkit, it may cause an issue. It may not, but basically I'll just kind of show you what happened to me personally so that you can hopefully avoid having to mess with all this. If I type nvidia.smi and I scroll up here, we will see my driver version, and we will also see a CUDA version, which for me is 12.4. Now, if I was to just go to the NVIDIA developer site right here and try to install CUDA toolkit, we see that this is version 12.8. If I download this and then try to build llama.cpp, it will fail because there will be a mismatch in compatibility between what's showing up here, which is CUDA version 12.4, and the 12.8. This actually did happen to me, and it was causing the build to fail because I had just aimlessly gone and installed the newest version. So you want to make sure that the CUDA Toolkit version you download matches what it says here in NVIDIA SMI or 12.4. In order to do that, from this page, you can just click Archive of Previous CUDA Releases, and we can then scroll down to find the one that actually lines up with the version we see here in NVIDIA SMI, which for my purposes would be 12.4. And then you click that, you see, okay, this is good. And you would basically just kind of follow along with this. So personally, I'm on Linux. I am on an x86-64 system, so I'm using an Intel i7-12700. My distribution is Ubuntu, and I am on 2022.04, and I would like to do a local installer. And then I basically would just run these commands to get the CUDA toolkit installed. I already have it installed, and I'm not going to play with like overwriting it or anything like that, but that is basically the general outline for how you would do that and then ensure compatibility, assuming you have an NVIDIA system that you are using this with. With that out of the way, and something I did just kind of want to cover because it gave me some trouble for a while with the version mismatch and things like that. We are basically now good to just go ahead and copy this and paste it into the terminal, which will then go ahead and kind of build llama.cpp for our system, which is what will allow us to actually go ahead and then subsequently run this full DeepSeek Dynamic Quant R1 version. Depending on your system and things like that, this could take a little bit of time and you may hear your fans ramp up. But once this is done, we can basically move on to the next step, which gets us closer to actually using the darn model, which is awesome. And once the build is complete, we will just see 100%, and then it will return us right here to our shell. Following this, the next thing to do is really going to actually be downloading these model files. Now, I'm definitely not showing that on camera because I already have them and it took like 4 hours to download. But there are, I suppose, a few different ways. So there is actually a way to do it through Hugging Face Hub here if you want to. However, personally, I just actually went ahead and manually downloaded these and saved them under a models DeepSeek R1, whatever schema this is. So I just saved them to a local folder like that. The only place that's really going to make a difference for you is when we actually go down here to run it, the model path will need to reflect where you actually saved these. So if we ran them through this Hugging Face Hub download thing, it would just kind of work as is because it would save them here. But if you manually placed them elsewhere, you will have to just kind of specify that here. With that out of the way, our next step, assuming we have now downloaded the models, of course, is to actually go ahead and run these. Now, the actual flags here are going to vary depending upon your system makeup. However, really kind of the main thing to be aware of there is the actual number of GPU layers here. So how many layers of the model you offload to your GPU will be dependent upon the GPU you have. As we can see here, it specifies one 24 gigabyte GPU. You would want to offload 7 layers. Now I have 2 of those, so I feel comfortable just changing this 7 to 14. And here's what we're going to do. We're actually going to go ahead and just open up a text editor to actually place this command into, so then we can easily modify it and things of that sort. So we can see here, I'm going to change the number of GPU layers to 14 to reflect the 48 gigabytes of graphics capability I have, if you will. And it says threads is how many CPU cores you have. Now, I have run this with 16 and it worked fine, but I've realized my 127K, my Intel i7 processor behind me has 12 cores, but it worked with 16 threads. So I think it has 20 total threads, but 12 cores. So I think this is referring to the amount of threads the processor has and not specifically the amount of cores. I apologize if that was a little more convoluted than need be. Following this, basically everything else we can kind of just not touch and leave the same. I suppose the recommended temperature from DeepSeek, I do recall reading somewhere here that it was 0.6. So that seems fine. We're not going to touch that. And basically, we're not going to touch anything else here, except I am going to change the prompt to reflect this full Flappy Bird prompt, because I suppose we are going to want to actually test this. So I will just go ahead and place that in between the tags right here. And man, we'll see what happens. The only other thing I need to do is, if you recall, we do need to actually point the model to the specific location on our system that it does exist within, which for me is right here. So I'm just going to open this in a terminal. I'm going to print the directory, and we will copy this and paste it here. Okay, and you might notice that that is not actually the full directory location, because we need to actually point it to the first of these 3 gguf files that we have downloaded. So I am just going to type / and then paste it, and then that should be the correct path for this to work with where I place the models on my system. Looking at this, perhaps it may just be simpler to follow with the Hugging Face hub download methodology that they had mentioned here, but you know. So basically what we're going to do now is go ahead and try to run this. And if we do this and paste it into our terminal, we are going to see that it is basically going ahead and beginning actually loading the model into our system and utilizing all of the special configurations and things that we had set with regards to how much to offload onto the GPU and things of that sort. This will inevitably take a good bit of time to actually get going, as this is the first run we are going to do with this. So I am likely going to time lapse it, but while I do that, I will just keep open first and foremost this, which is just think of as like I forget what that terminology, well, I don't remember what that thing was called in Windows, but just think of this as like what shows you your CPU and system RAM utilization. And then I will also keep NVIDIA SMI open so we can see the video card utilization in real time, but I will just make it update every 1 second by doing that. And then we will see, if we expand this, we will see both cards. So basically, I will just kind of leave these here as this goes ahead and loads, and we will be able to see how this all goes, assuming that it properly goes, and I'll time lapse it. All right, we can see that we saw a think tag there begin, which you're likely now familiar with in terms of some of these models, and it is actually going ahead and doing the generation, and it is responding to that big prompt. Truth be told, speed-wise, again, I know earlier when we were running this, I think we had ended up at 1.45 tokens per second. This really is not a horrible generation speed for a gigantic model of this size. And again, we are right now seeing the full DeepSeek R1 671 billion parameter model running on a local machine, which is awesome. And it's doing it relatively quickly. So obviously this entire output is going to likely take a fair bit of time. So I will again probably just time lapse this till it's done, and then we'll actually go ahead and test the prompt. But this is it's just cool. We can see total right now that this is using, again, I think we had touched upon this earlier, but it's using 92.5% of the available system RAM. So it's using 92.5% of 128 gigabytes of RAM. And then each graphics card is using 21 to 22 gigabytes of video RAM. All right, we can see that it has actually finished, and we got a total speed of 1.58 tokens per second. So a little faster than the original 1.45, which is cool. However, just quickly going through this code, I don't know that we actually are going to have received a successful result here, but I suppose more of this video was just actually about like architecturally being able to run this on the computer and how that went about happening and things like that. With that said, they do actually offer some of their runs and results for that specific prompt as well. If you go and actually click this here right above the thank you, and we can see here that if we want to scroll down, we can see, okay, so this is the non-dynamic quantization trial output. This is the dynamic quantization trial output. So from a more perhaps curiosity focused standpoint, this is actually really cool to see, because then you can actually go in yourself and see like, okay, how does it work with the non-quantized dynamic trial? And so basically, again, if we go back to the beginning where we explained like if we quantized our entire image, it would just all be blurry and a disaster. This is kind of what we're noticing here. And I'm kind of happy we clicked on that because it is kind of funny, but it also shows the power of this dynamic quantization. So based on that, this really is quite cool. And again, it does seem that we do, okay, so we have an else game over screen. Like I said, our code here does seem to be a bit different. However, it might work. I don't think it's going to. I'll probably just end up trying it just to see, but it is really cool just that this is all there. And just based on the fact that we're able to run a 671 billion parameter model locally on a non-heavy duty data center GPU equipped computer. I will just go ahead and try to run this right now just to see what happens, if nothing more. Like I said, I don't think it is going to work as is, but we will just kind of go ahead and try it, and it's probably not going to work, but you'll have to excuse my file naming capabilities are perhaps a bit nerfed from the factory. I don't know what you would want to make of that, but we will just go to desktop and ls. Okay, so that was a previous one that I tried that did not work either. And we are just going to try running this. Oh, cool. That's awesome. I am the fool because I discounted it. That is awesome. All right, let's try it again. I think it's the space bar. It did actually give the instructions at the end, I think. Restart by pressing space after game over. Oh, okay, so let's just... Oh, come on, that's just BS. How am I supposed to... Okay, so perhaps some of the pipe logic was not perhaps the best, but this is that's awesome. Okay, so we were actually able to accurately reproduce some of the results from the Unsloth page just on this in general. That is really probably going to conclude this video. I will have to edit it, and it'll probably take me a while because there was definitely a lot of like pausing and waiting for it to do things and things of that sort. But I suppose overall, for the kind of summary of this video, we were able to, thanks to the folks at Unsloth AI and their smart quantization methodology implemented on the full DeepSeek R1 671 billion parameter model, able to run this on our local machine and actually generate a working Flappy Bird game, which is absolutely cool. And I do believe, sure, I think like a Llama 370B would likely have also been able to have made this game. However, the really cool and important part of why having this model do it correctly is that it is the dynamic 1.58-bit quantization. So this model was shrunk 80% in size and still able to output a lucid game generation in a single shot, which is quite impressive and really, like, for someone like myself, quite exciting, I suppose we could say. So that really is going to sum this up. I hope this was cool to see. And yeah, like I said, I'm bad at outros, so I will do some more Jetson content, I promise. Some folks have given me some great ideas in the comments, so all right, thanks for watching.